Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Today we are going to discuss synthesis of aromatic compounds, SNAR, nucleophilic aromatic substitutions. Students, we are now going to discuss the synthesis of aromatic compounds, but the substitution which we are going to discuss in this lecture is nucleophilic aromatic substitution. So first is a brief introduction of nucleophilic aromatic substitution, the types, and then mechanistic approach, thinking mechanistically, then the retro of some of the few of the compounds, then thinking mechanistically, then nucleophilic aromatic substitution by the SN1 mechanism, then reagents for aromatic nucleophilic substitution on AR and 2 diazonium, 1 diazonium aromatic compounds, it is a type of SN1, then ortho and para products we shall be discussing. Nucleophilic aromatic substitution. What is nucleophilic aromatic substitution? Students, a nucleophilic aromatic substitution is a substitution reaction in organic chemistry in which the nucleophile displaces a good leaving group such as a halide on aromatic ring. दो conditions. पहले तो ये कि nucleophile आना चाहिए and it should displacing the leaving group, लेकिन वो कैसा leaving group हो? Good leaving group. Now you can see the diagram on right hand side, the upper one. Here a general nucleophilic substitution, aromatic nucleophilic substitution is shown. X is the halogen, a good leaving group. Nu negative is the nucleophile. Nucleophile is replacing, is displacing X. And the reactant on the left hand side of the equation there is X attached with aromatic ring, and on the right side of the equation nucleophile has displaced that good leaving group. There are 6 nucleophilic substitution mechanisms encountered with aromatic systems. Number 1 is SNAR, that is called addition elimination mechanism. The most important of these is the SNAR mechanism, where the electron withdrawing groups activate the ring towards nucleophilic attack. For example, if there are nitrofunctional group positioned ortho or para to the halide leaving group. Now you can see that in the reaction on the left hand side, lower one reaction, there is an electron withdrawing group attached on the aromatic ring. If it is attached on or a para position, then it will be activated towards the nucleophilic substitution, and that must be the good electron withdrawing groups should be attached on the aromatic ring to undergo SNAR. So as you can see, the nucleophile is coming. First the nucleophile is added, sigma complex is formed, both leaving group and nucleophile are here on the sigma complex, and then in the next step elimination of the leaving group is taking place. So that's why it is called addition elimination mechanism. In the first step the nucleophile is added, and in the second step the nucleophile is eliminated. Second one, nucleophilic substitution. Second one, nucleophilic aromatic substitution, is SN1 mechanism, that is encountered with diazonium salts. What is diazonium salt? There are 2 nitrogens attached to each other with a triple bond, and it is written as you can see in the right hand side reaction, upper one N2 plus. But if you open it, it will be N nitrogen, triple bond nitrogen, and the central one nitrogen will be positive due to making 4 bonds. Now the SN1 reaction is a substitution reaction in organic chemistry. SN stands for nucleophilic substitution, and 1 says the rate determining step is unimolecular. And if you remember, the unimolecular are two-step reaction and bimolecular are single-step reaction. So whenever there will be SN1, immediately there should be coming in the mind it is unimolecular, one molecular, and one molecular comes when there is only one molecule in the rate determining step. So if there is only one molecule that is responsible for the rate determination of the reaction, then of course there is a two-step reaction. In the next step, nucleophile is coming and attacking. In the first step, that is rate determining, only the Levy group. So in SN1 mechanism, there is a speciality of aromatic SN1 mechanism that is encountered with diazonium salts. Then the third one type is benzene mechanism, that is called E1CDADN. Arynes or benzynes are actually highly reactive species that are derived from an aromatic ring by the removal of two substituents. Now you can see that the reaction on the left side, reaction on the left hand, not on the left hand, this is the reaction on the right hand. The reaction on the right hand, the lower one reaction, there is a chloro attached with the aromatic ring, but with the use of sodamide in liquid ammonia, that chloro is replaced, and then a triple bond is formed between the carbon, which is steric, and the lower one carbon. So benzene has been detected, the intermediate benzene has been, this is benzene. Arynes or benzynes are highly reactive species derived from an aromatic ring by the removal of two substitute chlorine from the upper one, carbon which is a steric one, and hydrogen from the lower one has been removed to make this benzene. So this mechanism proceeds through the benzene intermediate, so that is called benzene mechanism, and then attacking nucleophile attached on the benzene ring. Then the other three nucleophilic substitution, aromatic nucleophilic substitution reactions, just you need to know by name even right now, because most of the concern will be the first three one, and if there will be any one of these three which I am going to just give you by name, so we shall be discussing that over there. The free radical SRN1 mechanism, the ANRORC mechanism, the viscous nucleophilic substitution. Alright, so got it? Now as we have seen the electrophilic substitution, aromatic substitution before, now if we are having substituents on the benzene ring, if we detach or we do the disconnection, then they are negative synthones, and they are synthones with the negative charge. Then we should go for thinking of nucleophilic aromatic substitution. Nucleophilic aromatic substitution means a nucleophile comes and replaces another nucleophile on the aromatic ring. So, or replaces hydrogen or substitutes hydrogen. Hydrogen is the leaving group, and nucleophile comes and attaches on the aromatic ring. In this case, when we think about the nucleophilic aromatic substitution, in this case, one point, as just as a review I want to discuss over here. Aromatic ring is having electron density, so it is normally negative. Negative means it is having rich in electron density, so most of the times it is electron rich, and electron rich is something that is that can act as an electrophile. So that can be attractive for an electrophile. So when nucleophile will come on benzene ring, for this the benzene ring should be a bit deficient in electron density, a bit positive character should be with aromatic ring. For that, if there are electron withdrawing groups on the benzene ring, that will make it potent for nucleophilic substitution. So, and the second one thing is that as far as nucleophilic aromatic substitutions were concerned, you have seen in the previous masters there were three major types you have seen for the nucleophilic substitution. One was the addition elimination mechanism, SNAR mechanism that is called. One was the SN1 mechanism, unimolecular aromatic nucleophilic substitution mechanism, and the third was the benzene mechanism. In the benzene mechanism, we have seen a very strong nucleophile was needed to remove or to be substituted on the benzene ring. And in SN1 mechanism, unimolecular aromatic nucleophilic substitution mechanism, diazonium must be there, and which can be any of the incoming nucleophile. The diazonium will be replaced by that incoming nucleophile for SN1 mechanism, and SNAR, any nucleophile that is coming will be replacing the halo group most probably on the aromatic ring. So that was just a review of the nucleophilic aromatic substitution. Now come to the slide. Here we see that there are two target molecules, 25 and 27. For both of these, if we disconnect C2O bond in 25 and we disconnect C2N bond in 27, we can have the same aromatic nucleus here, 26. So there should be a leaving group needed, and the other one, synthone, which is dated from 25 is OR negative, and from 27 is aniline or derivatives of aniline. So in both of the cases, the suggested reaction for the synthesis of 25 and 27 is nucleophilic substitution. When 26 will be reacting with OR negative alkoxy, then we shall get 25, and when aniline will be doing the nucleophilic substitution on 26, we shall get 27. So we can say, if we make the same disconnections as before, as we have done in the case of aromatic electrophilic aromatic substitution, the disconnections are the same like in 25 and 27, but the change of polarity we need electrophilic aromatic rings and nucleophilic reagents. First we were doing aromatic rings as they were having a bit electron density negative, and we were talking about the electrophilic reagents. But now here in this case we are talking about the nucleophilic reagents, and we are talking about the electrophilic aromatic rings. So we should need a leaving group X on the aromatic ring 26, and reagents such as alkoxides or amines are there. So for these synthones, alkoxides or amines and nucleophilic reagents are required, and aromatic ring will itself act as electrophilic aromatic ring. Now second point, you can check that nucleophilic reagents are behaving normally for alcohols or amines, but aromatic electrophiles present a problem. If like nucleophilic reagents, you know that the nucleophiles which attract the nucleus or positive charge, or which attracts the deficient molecules, nucleophiles, nucleus loving. positive charge loving are called the nucleophilic reagents. But how the aromatic ring can be electrophile? So benzene rings are, most of the times are nucleophilic, weakly nucleophilic, but they are nucleophilic. They are not electrophilic at all. Like in this reaction down, there is a nucleophile OR attacking on 28 and attacking on electron deficient position with which chloro is attached, and the resonance is taking place. 29 is being formed here. Now when negative charge on the oxygen of nitro will move back, then whole of the resonance will move back, and ultimately chlorine will be replaced from here, and 30 will be formed. Now we shall be discussing further about this on the next slide. Now look at structure number 31. There are two nitro groups. There are two nitro groups that are at ortho position to the leaving group. Leaving group over here is N diisopropyl diisopropyl amine or diisopropyl amine will be the synthone, you can say that. So diisopropyl N nitrogen with positive charge will be leaving from here after the disconnection. So how can we get it? We can get it very easily if we are having chlorobenzene and we do the nitration. So we can be guided in our choice of polarity by the nature of the target molecule. So the target molecule, if we do the disconnection here in 31, as there is a wiggly bond, you can see C2N disconnection. So how can we get this moiety? We can get this moiety where what moiety can we get from which it can be prepared? So we can think of the chlorobenzene here, 32, which can after reaction with diisopropylamine can give 31. So it does mean that when diisopropylamine is detached and we want to attack on the benzene ring, that should be, benzene should be electrophile in the nature. Benzene should be having a deficient character. So these two nitro groups are giving that electron deficient character to the ring 32. Now the lily pre-emergent herbicide trifluoralin B 31 has 3 electron withdrawing groups. So look at this. So many electron withdrawing groups are making aromatic ring potent for the nucleophilic aromatic substitution. So these 3 groups, 2 are the nitro groups and 1 is CF3 group, ortho para to the amine. In 32 we are discussing, in 32 has become ideal for nucleophilic substitution due to all these electron withdrawing groups. Now further 32 can be synthesized. If we do the retro, we consider that these nitros were not present over there. We do the disconnection of C2N bond, so the synthone for that was 33. 30T. We just by do the nitration of 33. Now that synthesis has been shown in the reaction given below. The synthesis is simply the nitration of the 33, and HCl is also produced in this reaction after the nitration. When chloro is after the nitration and nitro is substituted over here, then when nitro is substituted over here, HCl is not produced in this step. HCl is produced in the next step. After the nitration, we do the nucleophilic aromatic substitution with diisopropylamine. When we do the nucleophilic substitution, what will be there? Diisopropylamine will be attached at the position of chloro. It will be substituting the chloro, and HCl will be produced. That HCl that is produced will be making the will be acidifying the reaction, so that must be removed. So base is used to neutralize that HCl. This base is not used to deprotonate the amine, but it is used to remove HCl from there. Now it is obvious that the choice between the nucleophilic and electrophilic substitution must be mechanistically made. This is also true for the choice of all disconnections and synthones and reagents. Whatever disconnections are we making, whatever synthones are we making, whatever the reagents are we suggesting, whatever the reactions are we taking into the mind, all of these should be mechanistically made. Like, we should think about the mechanism, what is going on. So the formation of 31 is very easy because aryl chloride is activated by 3 groups. There are 2 nitro groups and 1 CF3 group. So the formation of 31 is very easy because electron withdrawing groups make the nucleophilic substitution reactions possible here. Now if we see the example, the reaction below, here is what? In this reaction, synthesis of fluoxetine, Prozac, a rather widely taken antidepressant, aryl ether. This is 34 about which I am talking. This is an aryl ether is an essential intermediate for the synthesis of fluoxetine, Prozac. Now we can think of 2 disconnections, one directly attached to the aromatic ring substituent and the other one which is the carbon to oxygen bond, B disconnection, as is shown. So B disconnection looks very attractive, as just only an SN2 reaction should work well for that. SN2 reaction can add up this substitution to the rest of the part. But what happens? Disconnection A is preferred over here because 34 is a pure enantiomer. It's a single enantiomer, and enantiomerically pure alcohol 36 is available. So if we are using enantiomerically pure reagent, so the reaction will be ultimately the 34 which will be formed from 36, and 35 will be enantiomerically pure. We should keep this in mind. We should think mechanistically for all these things. Now here, as you can see in 34, when we do the disconnection, we suggest 35. Now fluoride is here, as we know that fluoride is the worst leaving group among the halogens, as its C2F bond is very strong. So it is very rare to see SN2 reaction with fluoride as the leaving group. So yet it is the best choice for the nucleophilic aromatic substitution. So this is the best one choice for nucleophilic aromatic substitution, the fluoro leaving group, especially when the ring is weakly activated. As we can see here in 34, only CF3 group is attached, and come to 35, only CF3 is attached over here. Previously, when we in the previous example, when we have done nucleophilic substitution, that direction was very easy because 2 nitro groups and 1 CF3 was there, increasing its reactivity towards nucleophilic aromatic substitution. But here only 1 CF3 is here, so the fluoro will be very good leaving group in that case. Now we see mechanistically how fluoro is a good leaving group in the next slide. This is a 2-step reaction. The difficult step in this case is the addition of nucleophile. Aromaticity is destroyed in that case, and the intermediate is unstable anion. So the second step, 38, is fast. The fluorine accelerates the first step as is so electronegative, and it does not anion. Now if fluorine is attached over here, as we are saying that in nucleophilic substitution reactions there are two steps in the mechanism. First one is the attack of the nucleophile on the aromatic ring, and the second one is the leaving of the removal of the leaving group. So if we check here, fluoro makes it attracts the electron density of the aromatic ring and makes it potent for the attack of a nucleophile. So it accelerates the addition of the nucleophile on the aromatic ring. So if it is attacking, if the intermediate would be then a bit stabilized due to this electron withdrawing nature of the fluoro. Now the intermediate which is formed is an unstable anion due to the electron withdrawing effect of fluoro. That will be less unstable in that case if there is a fluoro substitute. And in the second step, what will be the 38, which will be like replacement of the fluoro group. That is a bit fast. So fluorine accelerates the first step as is so electronegative, and it does not does not that much unstable, the intermediate. The second step, 38, is fast. So fluorine accelerates the first step. Now, in the formation of trifluorylene 31, showed the amines are good nucleophiles for nucleophilic aromatic substitution. In the nucleophile here is an amine alcohol, that is 36. Direct reaction with 36 might lead to the formation of an amine instead of an ester. So if the 36 now the slide the number 36 was given in the previous slide. This is 36 amine alcohol which is attacking on 37 aromatic ring. So this negative ion is amine alcohol is 36. Amines are good nucleophiles here. Alcohol part of that is attacking actually on the aromatic ring. But if we just use it like this, the product can be, there are two now ends of the attacking nucleophile. One is amino group, and the other one is the alcoholic group. So amine is a good nucleophile, so there must be a chance that instead of ester formation, the amino group will attack on the aromatic ring, and that will be substituting the fluorine. So to avoid this, 36 is first treated with sodium hydride to make the oxy and ine, and then add to 35. The reason is that for the addition of oxy and ine, that it is a good nucleophile then as compared to the amine. So to making it a good nucleophile, sodium hydride is used. So the alcohol is less nucleophilic, but oxy and ine is more nucleophilic than amine. SN2 mechanism is not available for aromatic nucleophilic substitution.
This route is particularly
SN1 is providing we use the very best
easily added.
So in nucleophilic aromatic substitution, only SN1 is mechanism there, and
for the addition of cyanide,
chloro, copper. So SN1 mechanism, if you just review that SN1 mechanism,
usually give the best result.
Unimolecular reactions. And these are two-step reactions. In the first step, the attacking nucleophile attack, and in the second
electrophilic substitution, aromatic electrophilic substitution.
The leaving group.
They can be added to the aromatic ring
simultaneously. SN2 mechanism is not operating here in which both the attacking nucleophile.
These are nucleophiles, so they will not be.
So there is only SN1 mechanism.
It will not be possible to add them.
Now you can see
electrophilic addition.
In the reactions below,
in the case of
from the diazonium salt
46,
or when we do a gentle warming, the molecule of nitrogen is released. So the sequence for the nitration of an aromatic compound 39 to give 40, and then
diazonium salt of 47
nitrating 39 nitro
so the
aromatic compound 40 will be achieved, and then upon the reduction of this 40
this connection of 46
palladium over charcoal, hydrogenation in the presence of palladium over
47 is having
carbon,
like we have
gives
described it, and then we have done
and then making a diazonium salt of that, and which after reduction 41 is obtained, in which NO2 has been converted into nitro has been converted into imine.
So from
now this upon diazotization, this amino group is converted into diazonium salt, and then afterwards, so diazonium salt and the reagents used for making diazonium salt are sodium nitride and HCl. So nitrous acid is basically the reagent
toluene can be nitrated, so
giving an O plus
reaction can give us a toluene.
So it attacks
can give us 48 from toluene. Now if we check the synthesis, that is very straightforward.
So the diazonium salt 42 is stable at only 0 to 5
would not
it decomposes
out the first two steps as the
and unstable arise at
we do not draw the diazonium salt
warming to room temperature. If you keep the temperature from 0 to 5, diazonium salt will remain. But if you will increase the temperature, it will be decomposed, giving nitrogen gas and unstable arise at time 43. So when the temperature will be increased, the transformation from 42
in this
A to 43 will take place, as you can see from here. So the empty orbital of carbon in 43, that is an sp2 orbital. And that is in the plane of the aromatic ring, because it is attached with the carbon, it is the orbital of a carbon-to-carbon double bond. That carbon is basically sp2 hybridized. So this is an sp2 orbital, and it is in the plane of the aromatic ring. But in the case of cation, aliphatic or alkyl chain, that was that empty orbital was not in the plane, because that carbon was having already 3 substituents, and that empty orbital was not lying in the plane of those substituents. But in the case of aromatic ring, carbon-carbon double bond is having this empty orbital, and that is in plane of the aromatic ring.
Now, as far as reagents for aromatic nucleophilic substituents are concerned, a table is given here after the reaction. As we know that the aromatic nucleophilic substitution starts from an amine, primary amine, that is diazotized. 41 here is shown, structure number 41, that is diazotized at 5 degrees centigrade, and then after the diazotization 42 intermediate is formed, and then reagents, whatever the nucleophiles are there, they attack, and then 49 is formed, that is the attachment of that nucleophile and the removal of N2 gas. Now if you want to show the disconnection zone 49, for example, the syntones which can be formed are OH, OR, that can be substituted in the place of Z, OA in 49, and in the list of syntones I am just going through: OH, OR, cyano, chlorobromoido, aromatic H, simple H. So the reagent for these can be water, alcohol, cuprous cyanide, cuprous chloride, cuprous bromide, potassium iodide, aromatic compound, can be benzene even, and then phosphoric acid or ethanol or H positive. Ethanol in the acidic medium. Now For all of these, some commands are given: water and hydroxyl water and alcohol. When the reagents are used, this is probably a SN1 reaction. When there are reagents like cuprous, cyanide, chloride, bromide, that can be a radical reaction. Potassium iodide, that is the best way to add iodine, Friedrich-Kappa relation, the second last one, and that is the Friedrich-Kappa relation means adding aryl group along with the aromatic system, along with the aromatic ring in the place of C. So, and then the last one is the reduction of diazonium. Means in the reduction of diazonium, what we do, when we do reduction of diazonium, this N2 will be reduced. So that will be substituted by hydrogen in the presence of phosphoric acid or acidified ethanol. Here the discussion of two products, ortho and para mixture, is discussed here. When we do the nitration of toluene, both para-nitro, that was shown in the structure 4 para-nitro, and ortho-nitro compounds are formed. In fact, the reaction gives a mixture. So this is acceptable because providing these compounds can be separated, especially if the industry does a job on a very large scale, as here, like in the synthesis of a sweetener, saccharine. That is a good example for that. Saccharine, compound 50, is a cyclic imide, that a double amide from one nitrogen atom and two acids. That is double amide from one. There is a one nitrogen atom and there are two acids which are making bond with that nitrogen. If we disconnect C to N bond and S to N bonds, the two acids, one carboxylic acid and one sulfonic acid, are revealed. Structure 51. Now FGI convert one of them into ortho-para directing groups, and we can use the same oxidation reaction we met at the start. So now 52 can be made by sulfonation. What did we do? If you remember that when we were going to disconnect the the benzoic acid in the previous slides we've seen, we did say that disconnecting the C to C bond of the carboxylic acid is not a good reaction. It will not give a good reaction to construct this benzoic acid. So what we do FGI. We did FGI at that time also. Then we have produced the benzoic acid or carboxylic group on the aromatic ring by the oxidation of methyl. So we can take toluene. So now if we do the disconnection of C to S bond in 52, we can get this from 50. We can get this 52 from toluene. We can do the sulfonation of toluene, and we can get 52. In practice, chlorosulfonic acid is used as this gives the sulfonyl chloride directly. So now if we are thinking that chlorine might be the best leaving group, so but there is no Lewis acid here, so instead a very strong chlorosulfonic acid protonates itself to provide a molecule of water as a leaving group. So from what can we do from the toluene? The toluene can be reacted with chlorosulfonic acid to give 53 sulfonation. Chlorosulfonyl group is added, and then two isomers have been formed, ortho and para. Now the thing which I have mentioned here, that chloro is a good leaving group, but in the case when there is no leaves acid here, so this will not leave like that. So chlorosulfonic acid protonates itself to provide a molecule of water as leaving group. So now here water is removed from here, and the replacement of H from here and OH from chlorosulfonic acid will remove water from here, or from full of the reaction I am talking about, but actually chlorosulfonic acid ClSO2OH, OH from here and H that is used for the protonation of chlorosulfonic acid. The water will be removed from here first, and afterwards the full reaction is the replacement of hydrogen by chlorosulfonyl group. Now the reaction gives a mixture of ortho 53 and para 54 plus the ortho compound. The ortho compound is converted into saccharine by the reaction with ammonia. So if we do the reaction of 53 with ammonia, then that Cl is replaced by ammonia. Then if we do the oxidation of the reaction of with ammonia and oxidation and the para compound toluene sulfonyl chloride 54 para compound, that is toluene sulfonyl chloride 54 orthosyl chloride, is sold as a reason for converting alcohols into leaving groups. So there is no way we can get this 53 by this route. The para compound, the toluene sulfonyl chloride is actually orthosyl chloride. Para compound toluene sulfonyl chloride 54. The orthosyl chloride is common. It will be used for the in the market as a reagent for converting alcohols into leaving groups, and 53 will be converted by the reaction with ammonia into 55, and then will be oxidized with the KMnO4 to give 56, and then will be heated to give the imide 50, that is saccharine.